Okay, so today in class we left off with this example. We want to know what the radius of curvature at the bottom of the first Superman hill. So we have the Superman ride that looks something like this, and we're looking at the bottom if we assume that we are traveling in that direction. And we want the acceleration to be no more than 3 g's. So A is equal to 3 times 9.8 worth of acceleration. So we have v, we have a velocity of 30 meters per second, and we want to know what r must be. So we know the relationship between a, v, and r is a equals v squared over r. So rearranging that gives us r equals v squared over a. And so we have 30 squared divided by 3 times 9.8. And that gets us a radius of curvature of 30.6 meters. So that is the minimum radius that ride can be at the bottom of the hill. Now, if I go ahead and talk more about the direction of the net force and the acceleration, at the bottom of the hill we must have an acceleration that is up, because at the bottom of the hill, directed towards the center of the circle, so if we kind of imagine that we have a circle like this, towards the center, the inward acceleration is up. So the net force must be up, meaning that we have a downward force of gravity and we have an upward normal force that must be larger in order, so in this case F of n is greater than F sub g in order for there to be an acceleration towards the center. So if we look further into what we were addressing today in class was what causes an object, allows an object to move in a circle around a curve in the first place. Well, there must be some sort of net force, okay, because we said that there's an acceleration. Without it, the objects would move at a constant velocity. So a constant velocity means a constant speed in a straight line. So we talked about some of the examples today and described the forces that were acting on them. Now I want to kind of look at it in a slightly different light. So the question now has, or the statement we have two different ways to approach centripetal motion. We have the acceleration, which is a supply due to a net force, and then we have a demand due to the speed and radius of curvature. So the supply is just the sum of the forces, and this is going to change just like before depending on the situation. What are the objects that are acting on your, what are the actions that are acting on your object? And the demand is equal to ma, but we said a here is equal to v squared over r. So substituting that in, we get m times v squared divided by r. So this is the equation that we'll be using for circular motion. Your F net is equal to mv squared over r. So let's take a look at a problem here. We have a mass of 600 kilograms. Race car wants to travel 15 meters per second around a 120 meter radius curve. If the force of friction is 4,800 newtons, will the driver have to slow down in order to not skid around the track? So the supply force is due to friction, which we have an amount of static friction to be 4,800 newtons. The demand is my mv squared over r. That is 600, the mass, times 50 meters per second squared divided by my radius of 120 meters. So the demand is 12,500 newtons. So the question is, if we have a supply of 4,800 but the demand is 12,000, then yes, we must absolutely have to slow down in order to make it around the turn. So another way of asking it, okay, so we know that 50 meters per second is too fast around a 120 meter radius curve. So what is the maximum speed? So if we think of it as that we have some amount of force, okay, the 4,800 newtons due to the friction, we want to know what is the maximum V that's allowed. So if we solve for V here, we cross multiply by R. So we have R times the frictional force, and then we divide by M. And that is equal to V squared, and then of course, if you square root both sides, I get the square root of 120 meters times 4,800 newtons divided by my mass of 600 kilograms. And so I get a maximum speed of 30.8 meters per second, so it's approximately 31. Which makes sense because 31 is obviously less than 50, so we slowed down and we were able to make it around the turn. So now the next kind of logical argument is, what if we reduce the mass? Well, if we look at this, if we can at first glance say, well, if we make the mass smaller, let me rewrite this. If I make the mass smaller, then yeah, the supply force must be smaller. But we have to ask ourselves, what is causing that car to go around the turn? So if we draw the free body diagram for the car going around the turn, we have the force of gravity and the force of normal, so those are two equal. And let's assume that they're making a right turn, then there must be some rightward frictional force. And so this is what's allowing the car to make that right turn, but we calculate this by mu times the normal. Okay, the fun equation. But if the force of gravity is mg, and then the normal is also mg. And if we put mg in for the normal, this becomes mu mg is equal to my friction. So then if we go back up to the supply and demand, on the supply side we have the friction, and on the demand side we have the mv squared over r. Well, if the friction is equal to mu mg, then we have mu times m times g equal to mv squared over r. And what you can see here is that there's an m on both sides, so that even though if I reduce the mass, the maximum speed now, if I multiply by r and then take the square root, the maximum speed is equal to the square root of r times mu times g, with no, so there's a little bit of a note here, there's no mass, meaning that the mass does not make a difference. So the answer to the question is no. Okay, so that's all for now. We'll apply this some more tomorrow, and take care. Have a good night. Bye-bye.